An electric locomotive is a locomotive powered by electricity from overhead lines, a third rail or on-board energy storage such as a battery or fuel cell. Electric locomotives with on-board fueled prime movers, such as diesel engines or gas turbines, are classed as diesel-electric or gas turbine-electric locomotives because the electric generator-motor combination serves only as a power transmission system. Electricity is used to eliminate smoke and take advantage of the high efficiency of electric motors. But the cost of electrification means that usually only heavily used lines can be electrified. Characteristics: one advantage of electrification is the lack of pollution from the locomotives. Electrification results in higher performance, lower maintenance costs and lower energy costs. Power plants, even if they burn fossil fuels, are far cleaner than mobile sources such as locomotive engines. The power can come from clean or renewable sources, including geothermal power, hydroelectric power, nuclear power, solar power and wind turbines. Electric locomotives are quiet compared to diesel locomotives since there is no engine and exhaust noise and less mechanical noise. The lack of reciprocating parts means electric locomotives are easier on the track, reducing track maintenance. Power plant capacity is far greater than any individual locomotive uses, so electric locomotives can have a higher power output than diesel locomotives, and they can produce even higher short-term surge power for fast acceleration. Electric locomotives are ideal for commuter rail service with frequent stops. They are used on high-speed lines, such as ICE in Germany, Acela in the US, Shinkansen in Japan, China Railway High-Speed in China and TGV in France. Electric locomotives are used on freight routes with consistently high traffic volumes, or in areas with advanced rail networks. Electric locomotives benefit from the high efficiency of electric motors, often above 90%. Additional efficiency can be gained from regenerative braking, which allows kinetic energy to be recovered during braking to put power back on the line. Newer electric locomotives use AC motor inverter drive systems that provide for regenerative braking. The chief disadvantage of electrification is the cost for infrastructure. Overhead lines or third rail, substations, and control systems. Public policy in the U.S. interferes with electrification. Higher property taxes are imposed on privately owned rail facilities if they are electrified. U.S. regulations on diesel locomotives are very weak compared to regulations on automobile emissions or power plant emissions. In Europe and elsewhere, railway networks are considered part of the national transport infrastructure, just like roads, highways and waterways, so are often financed by the state. Operators of the rolling stock pay fees according to rail use. This makes possible the large investments required for the technically, and in the long term also, economically advantageous electrification. Because railroad infrastructure is privately owned in the U.S., railroads are unwilling to make the necessary investments for electrification. History: the first known electric locomotive was built in 1837 by chemist Robert Davidson of Aberdeen. It was powered by galvanic cells. Davidson later built a larger locomotive named Galvani, exhibited at the Royal Scottish Society of Arts exhibition in 1841. The 7-ton vehicle had two direct-drive reluctance motors, with fixed electromagnets acting on iron bars attached to a wooden cylinder on each axle, and simple commutators. It hauled a load of 6 tons at 4 miles per hour for a distance of 1.5 miles. It was tested on the Edinburgh and Glasgow Railway in September of the following year, but the limited power from batteries prevented its general use. It was destroyed by railway workers, who saw it as a threat to their security of employment. The first electric passenger train was presented by Werner von Siemens at Berlin in 1879. The locomotive was driven by a 2.2 kilowatts series wound motor, and the train, consisting of the locomotive and 3 cars, reached a speed of 13 kilometers per hour. During 4 months, the train carried 90,000 passengers on a 300-meter-long circular track. The electricity was supplied through a third insulated rail between the tracks. A contact roller was used to collect the electricity. The world's first electric tram line opened in Lichterfelde near Berlin, Germany, in 1881. It was built by Werner von Siemens. Volks Electric Railway opened in 1883 in Brighton. Also in 1883, Modling and Hinterbrühl tram opened near Vienna in Austria. It was the first in the world in regular service powered from an overhead line. 5 years later, in the U.S., electric trolleys were pioneered in 1888 on the Richmond Union Passenger Railway, using equipment designed by Frank J. Sprague. Much of the early development of electric locomotion was driven by the increasing use of tunnels, particularly in urban areas. Smoke from steam locomotives was noxious, and municipalities were increasingly inclined to prohibit their use within their limits. The first electrically worked underground line was the City and South London Railway, prompted by a clause in its Enabling Act prohibiting use of steam power. It opened in 1890, using electric locomotives built by Mather and Platt. Electricity quickly became the power supply of choice for subways, abetted by the Sprague's invention of multiple-unit train control in 1897. Surface and elevated rapid transit systems generally used steam until forced to convert by ordnance. The first use of electrification on a main line was on a 4-mile stretch of the Baltimore Belt Line of the Baltimore and Ohio Railroad in 1895, connecting the main portion of the B&O to the new line to New York through a series of tunnels around the edges of Baltimore's downtown. 3 BO+BO units were initially used. At the south end of the electrified section, they coupled onto the locomotive in train and pulled it through the tunnels. Railroad entrances to New York City required similar tunnels, and the smoke problems were more acute there. A collision in the Park Avenue Tunnel in 1902 led the New York State Legislature to outlaw the use of smoke-generating locomotives south of the Harlem River after 1 July 1908. In response, electric locomotives began operation in 1904 on the New York Central Railroad. In the 1930s, the Pennsylvania Railroad, which had introduced electric locomotives because of the NYC regulation, electrified its entire territory east of Harrisburg, Pennsylvania. The Chicago, Milwaukee, St. Paul and Pacific Railroad, the last transcontinental line to be built, electrified its lines across the Rocky Mountains and to the Pacific Ocean starting in 1915. A few East Coast lines, notably the Virginian Railway and the Norfolk and Western Railway, electrified short sections of their mountain crossings. However, by this point electrification in the United States was more associated with dense urban traffic, and the use of electric locomotives declined in the face of dieselization. Diesels shared some of the electric locomotive's advantages over steam and the cost of building and maintaining the power supply infrastructure, which discouraged new installations, brought on the elimination of most mainline electrification outside the Northeast. Except for a few captive systems, by 2000 electrification was confined to the Northeast Corridor and some commuter service. Even there, freight service was handled by diesels. Development continued in Europe, where electrification was widespread. Introduction of alternating current. The first practical AC electric locomotive was designed by Charles Brown, then working for Oerlikon, Zurich. In 1891, Brown had demonstrated long-distance power transmission, using three-phase AC, between a hydroelectric plant at Laufen am Neckar and Frankfurt am Main West, a distance of 280 kilometers. Using experience he had gained while working for John Heilmann on steam electric locomotive designs, Brown observed that three-phase motors had a higher power-to-weight ratio than DC motors and, because of the absence of a commutator, were simpler to manufacture and maintain. However, they were much larger than the DC motors of the time and could not be mounted in underfloor bogies. They could only be carried within locomotive bodies. In 1894, Hungarian engineer Kálmán Kanda developed high-voltage three-phase AC motors and generators for electric locomotives. Kanda later invented the rotary phase converter, enabling electric locomotives to use three-phase motors whilst supplied via a single overhead wire, carrying single-phase AC. In 1896, Olicon installed the first commercial example of the system on the Lugano tramway. Each 30-ton locomotive had two 110 kW motors run by three-phase 750 V 40 Hz fed from double overhead lines. Three-phase motors run at constant speed and provide regenerative braking, and are well suited to steeply graded routes. And the first mainline three-phase locomotives were supplied by Brown in 1899 on the 40 km Bergdorf-Thun line, Switzerland. The first implementation of industrial frequency single-phase AC supply for locomotives came from Olicon in 1901. Using the designs of Hans Ben Eschenberg and Emil Huber Stocker, installation on the Seebach-Wettingen line of the Swiss Federal Railways was completed in 1904. The 15 kV, 50 Hz, 345 kW, 48-ton locomotives used transformers and rotary converters to power DC traction motors. In 1896 to 1898, Kanda designed a short three-phase AC tramway in Evian-les-Bains. Italian railways were the first in the world to introduce electric traction for the entire length of a main line rather than just a short stretch. The 106 km Valtellina line was opened on 4 September 1902, designed by Kanda and a team from the Ganz Works. The electrical system was three-phase at 3 kV, 15 Hz. The voltage was significantly higher than used earlier and it required new designs for electric motors and switching devices. The three-phase two-wire system was used on several railways in northern Italy and became known as the Italian system. Kanda was invited in 1905 to undertake the management of Società Italiana Westinghouse and led the development of several Italian electric locomotives. During the period of electrification of the Italian railways, tests were made as to which type of power to use. In some sections there was a 3600 V 16 and 2/3 Hz three-phase power supply, in others there was 1500 V DC, 3 kV DC and 10 kV AC 45 Hz supply. After WW2, 3 kV DC power was chosen for the entire Italian railway system. 1500 VDC is still used on some lines near France and 25 kV 50 Hz is used by high-speed trains. A later development of Kanda, working with both the Ganz Works and Società Italiana Westinghouse, was an electromechanical converter, allowing the use of three-phase motors from single-phase AC, eliminating the need for two overhead wires. In 1923, the first phase converter locomotive in Hungary was constructed on the basis of Kanda's designs and serial production began soon after. The first installation, at 16 kV 50 Hz, was in 1932 on the 56 km section of the Hungarian state railways between Budapest and Komárom. This proved successful and the electrification was extended to Hegyalom in 1934. In Europe, electrification projects initially focused on mountainous regions for several reasons. Coal supplies were difficult, hydroelectric power was readily available, and electric locomotives gave more traction on steeper lines. This was particularly applicable in Switzerland, where close to 100% of lines are electrified. An important contribution to the wider adoption of AC traction came from SNCF of France after World War II. The company had assessed the industrial frequency AC line routed through the steep Hollental Valley, Germany, which was under French administration following the war. After trials, the company decided that the performance of AC locomotives was sufficiently developed to allow all its future installations, regardless of terrain, to be of this standard, with its associated cheaper and more efficient infrastructure. The SNCF decision, ignoring as it did the 2,000 miles of high-voltage DC already installed on French routes, was influential in the standard selected for other countries in Europe. The 1960s saw the electrification of many European main lines. European electric locomotive technology had improved steadily from the 1920s onwards. By comparison, the Milwaukee Road Class EP2 weighed 240 t, with a power of 3,330 kilowatts and a maximum speed of 112 km per hour. In 1935, German E18 had a power of 2,800 kilowatts, but weighed only 108 tons and had a maximum speed of 150 km per hour. On 29 March 1955, French locomotive CC 7107 reached 331 km per hour. In 1960, the SJ-class DM3 locomotives on Swedish railways produced a record 7,200 kilowatts. Locomotives capable of commercial passenger service at 200 km per hour appeared in Germany and France in the same period. Further improvements resulted from the introduction of electronic control systems, which permitted the use of increasingly lighter and more powerful motors that could be fitted inside the bogies. In the 1980s, development of very high-speed service brought further electrification. The Japanese Shinkansen and the French TGV were the first systems for which devoted high-speed lines were built from scratch. Similar programs were undertaken in Italy, Germany and Spain. In the United States, the only new mainline service was an extension of electrification over the Northeast Corridor from New Haven, Connecticut to Boston, Massachusetts, though new electric light rail systems continued to be built. On 2 September 2006, a standard production Siemens electric locomotive of the Eurosprinter type ES64U4 achieved 357 km per hour. The record for a locomotive-hauled train on the new line between Ingolstadt and Nuremberg.